All right, hey AP Chemistry. So I had a question about this mechanism part two for the rate law from the free response question for day three. And so I wrote some information on top here. We had determined, or you had determined in a previous step in part B, that the rate law was second order with respect to NO2. So rate equals K NO2 squared. And this is the original chemical reaction. 2NO2 yields 2NO plus O2. And that's because in part B there were a bunch of graphs, and here's what the question looks like. There were a bunch of graphs, and you found out that the rate of 1 over the concentration of NO2 was linear. And that means if it's linear with respect to 1 over NO2 versus over a time, that means it's second order. So when my graph is linear with 1 over the concentration of time, it's second order. If it was linear with respect to natural log, first order. If it was linear with just changing concentration, that's zeroth order. Mechanism 1, I'm sure, was fine because you just use the slow step, boom, done. You determine it does match the rate law. But mechanism 2 is a little bit more complicated. So for mechanism number 2, we have step 1 that has NO2 in equilibrium with N2O4, and it says that it's a fast equilibrium. Then we have N2O4 yields 2NO plus O2, and that's our slow step. The way we write rate laws is from our slow step. So I'm going to write the rate law from the slow step. We have N2O4, and is one of them. So if I want to begin to write the rate law, I'll write rate equals K N2O4. Okay? I'm going to call this 2. So I'm going to say K2. Now, this is a problem because we cannot write, this is an intermediate. How do I know it's an intermediate? It shows up in the first step, gets used in the second. An intermediate is made in the middle of a reaction. If it was a catalyst, it would be used in the first step and then spit out in the last step over here. So it would be used as a reactant, spat out as a product if it was a catalyst. But since this is an intermediate, it's made first and then used up. I have it in my rate law. I can't have intermediates in rate laws. Now, if you want to know why, these concentrations are going to be hard to determine because not only is it being used up, it's being made, used up, and made. It's going to be hard to get that concentration. So I cannot and don't want to include an intermediate in my rate law. So I have to somehow get rid of this. I have to get rid of brackets N2O4. So how am I going to do that? Well, you're going to do what the AP Chemistry curriculum calls the Steady-State Approximation. You're going to look at the previous step. You're going to find where N2O4 is. N2O4 is in my previous fast equilibrium step. Remember, and I'm going to write this as K forward, K reversed. You probably can't see that, but I put KF over KR. It's an equilibrium. So there's a forward and reversibility to this reaction. And so I have NO2 and NO2 turning into N2O4, but then I also have simultaneously N2O4 turning into NO2 and NO2. So I can write, I'm going to put this on the side here, I could write a rate law for the forward and the reverse reaction. Typically we write rate laws for reactants turning into products, but I'll have that twice. I'll have NO2 turning into N2O4, and I'll have N2O4 turning into two NO2s. So let me write rate of the forward. That's becoming a mess. So I'm going to write rate of the forward is equal to KF. For the forward, it's just NO2, and there's two of them, so it'd be like NO2 squared. So for the forward reaction, the coefficient that technically would go here, this would be 2 NO2 yes, technically. So that 2 ends up being my exponent. So NO2 squared. For my K of my reverse, in the reverse direction, reverse can say that this acts as a reactant and turns into these products back and forth. I could write that reaction both ways. So I could actually write a rate law with respect to the reverse reaction. Rate of the reverse is equal to KR, concentration of N2O4, and there's only one of them. So it would only get a power of 1. Now, what do we need to remember about equilibrium? Now, I brought this up in Unit 5, and it definitely comes up in Unit 7. You have to know the definition of equilibrium. It's not that these concentrations are going to be equal, but in equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. If these two rates are equal, What else must be equal? These two things. So rate of forward is equal to the rate of the reverse, and that's the definition of equilibrium, when the rates are equal to each other. So how these two are turning into N2O4 at the same rate, change in concentration over change in time, N2O4 is turning into NO2. So now since these two are equal, these two are equal. So I could write Kf NO2 squared equals Kr N2O4. These two are equal now. This rate law is equal to that rate law, right? So the rate is going to be equal to K, which is some constant, times the concentration squared. This rate is going to be equal to some constant times the concentration. So these numbers are equal. I can write them like this. And now, remember what I said previously, I need to find some expression to kind of combine to get rid of this N2O4. I need N2O4 in terms of reactants or products that are in my chemical reaction. Specifically, I'm going to need somehow to get N2O4 to have reactants that are involved in my chemical reaction. In order for me to do that, I'm going to be using this expression here. I could rearrange and get N2O4 by itself. How can I do that? Well, Kr is a constant. This is kind of like if I had 5 times x. How do I get x by itself? You would divide both sides by 5 or divide both sides by Kr. So if I divide both sides by Kr, these cancel out, I will get that the brackets N2O4, is equal to Kf over Kr brackets NO2 squared. Now, just like I said this a couple times, this is like algebra. All I have to do is plug in this expression into here. I'm going to plug in and say, I'm going to put this into this expression. So now I know that brackets N2O4, or the concentration of N2O4, is equal to Kf over Kr NO2 squared, because I had rearranged and solved for it over here. Plugging and chugging it in, I'll have K2, and then I'll put this whole thing in here. Oops, I don't want to get rid of the 2. And so now this will be Kf Kr NO2 squared. Now the complicated thing here is that I have K2, Kf, and Kr multiplied all times NO2 squared. These are constants. So remember, in algebra or in any type of math class, you are allowed to combine like terms or combine constants. All of these constants can just become one big thing. I'm going to do that in 2 steps. So technically I have K2 times Kf over Kr, concentration or brackets NO2 squared is beginning to be my rate law. All of these K's are just one big constant that get combined. So I could just call them K prime or something. I just call it K. It's a combined K. NO2 squared. And that will be my rate law with respect to N2O4. Now, does this rate law now that I get after making this approximation and plugging it in, does it match my original rate law? And it does. NO2 squared, NO2 squared. This K doesn't matter. This K is a constant. So this K is a constant, gets all combined, and I have a rate law that matches. This is known as the steady-state approximation to AP chemistry, where you have an intermediate in a fast equilibrium, and you have to solve for it in order to plug it back into a rate law that has something that's in my chemical reaction. Is NO2 in my original chemical reaction? Yes, NO2 is a reactant in my original chemical reaction. All right, so hopefully that video was helpful. This is probably one of the most complicated type of mechanisms that you're going to have to know for AP chemistry, using what we call the steady-state approximation with a fast equilibrium. If you still have any questions or concerns, please let me know.